Hello everyone. Today we will be presenting on the thermodynamics part of our integrated project. Next slide, please. We are group 19 and we consist of 4 members, which are Jashmen Reuben, Ying Huey, Siti Khaleelah, and Fatih Nadhir. For your information, Fatih Nadhir will not be joining us today because he is only responsible for the process heat transfer part. Next slide, please. For our presentation today, we have divided it into four parts, namely the introduction, process description, calculation and discussion, and lastly, the conclusion and recommendations. Next slide, please. As you can see in this photo, it is a steam power plant. The utilization of steam power plants are in a wide range throughout the world for electricity generation. In fact, 80% of electricity in the world is produced from fossil fuels, mainly coal. Common analysis method used is the first law and the second law of thermodynamics. A steam power plant consists of 4 steady flow devices, namely the boiler, turbines, heat exchanger, and the pump. For this case study, we are designated to build a steam power plant using Campro Waja TRL-12 50 megawatt steam turbines. Next slide, please. As you can see here, this is our schematic diagram of the steam power plant. It consists of the boiler, turbines, condenser, and the pump. Next slide, please. So, these are the stream specifications of our steam power plant. As you can see in stream 1, stream 1 enters the boiler as a compressed liquid at 30 megapascals. Constant pressure heat addition in the boiler makes the exit pressure of the boiler to be the same, which is 30 megapascals, and with a temperature of 600 degrees. With these conditions, the working fluid, which is water, will be in a superheated vapor state. And then this stream enters the turbine, and then the water enters the water enters the turbine, and it rotates the working shaft connected to an electricity generator. So when the water exits the turbine, it will be at 180 degrees and 1 megapascal with the state of a vapor liquid mixture. And then this stream enters the condenser, and then there will be a constant pressure heat rejection in the condenser. Hence, when the water exits the condenser, it will also be in 1 megapascal. The temperature will be at 95 degrees, and it will be in a compressed liquid state. This stream will then once enter the pump again and complete the cycle. So now I will pass the so next slide, please. And this is the state of the working fluid of our steam power plant. As you can see, cold water enters the boiler and then exits the boiler at a higher pressure and exits the boiler at a constant pressure but with a higher temperature, and it exits the turbine at a lower temperature, and then it enters the condenser, and then there will be a heat rejection, and the water will be cooled down, and then it will enter the pump, and the cycle continues. Now I'll pass the floor to Reuben.
Okay, so I'll be explaining on the calculation and discussion done on the analytic designed steam power plant. So before I go further, I would like to share some of the specification used in the So as you have seen in the schematic diagram before, there are 6 turbines are installed so that we can produce the designated electricity of 280 megawatts. And the proposed steam power plant was designed using Aspen HYSYS. And the values of enthalpies and parameters were referred and taken from the property table. And the analysis of the steam power plants were analyzed using the application of first and second law of thermodynamics. And the power plant design is also designed as such adheres to the actual Rankine cycle. So following on, these are the values from the Aspen HYSYS where we we got all the values we needed. For example, the QH, QL, work output of turbine and work input of pump, and the total volume flow rate of the system. Moving on to the first steady flow devices, boiler. So in the boiler, heat from the burning coal in the furnace is transferred to the working fluid. And the system boundary in this system is the boiler. So the heat process of the liquid undergoes an isobatic heat supply, as said before. So the enthalpy of the inlet and the outlet stream was calculated using the parameters with referring to the property, and we were managed to prove through the manual calculation that we got the Q in as also same with the Q in gotten from the Aspen HYSYS. Moving on to the turbine. The turbine analysis is only made for one turbine uh, for the manual calculation. So in the turbine, the superheated steam from the boiler undergoes isentropic expansion in turbine, and the entropy of the steam remains constant. So at this point, the turbine is assumed to have negligible kinetic energy and also potential energy. So the enthalpies of the inlet stream and the outlet stream was also calculated using the parameters and based on the property table, and we managed to get the work output of one turbine 15 megawatts approximately, and as I told earlier, 6 turbines are installed, so the total work output produced by the turbine is 300 megawatts. Following on, the heat exchanger used in our steam power plant is the air-cooled condenser. So in here, the mixture state steam from the turbine enters the heat exchanger and undergoes isobaric cooling process, where the heat is rejected from the working fluid. So the analysis was made to calculate the amount of heat rejected, and by calculating the enthalpy of the inlet and outlet stream of the heat exchanger using the parameters, and by also using the property table, we managed to prove the heat rejected value is same as the one we got from the Aspen HYSYS simulation as well. Last but not the least, the final steady flow device to be analyzed is the pump. So in the pump, the compressed liquid undergoes an isotropic compression process, where the external work is supplied to the pump, so that the work is done on the working fluid by the means of pump operation. So this analysis is made to calculate the work input that is supplied to the pump. So by calculating the enthalpy of the inlet and outlet stream of the pump, we managed to prove with the manual calculation the work input of the pump is 20.24 megawatts, which same with the value got from the Aspen HYSYS. So by all the analysis made, we can finally determine the thermal efficiency of the designed steam power plant. So the W net out, which given by the formula where the work turbine minus the produced by pump and the fan. The work fan in this case is by the heat exchanger, as if we are using a air-cooled condenser, where there will be a fan to induce the air for the cooling process. The work of the fan was taken from a source that is already cited over there. So using all the information available, we managed to get the W net out is 200 megawatts as designated. So using the thermal efficiency formula, we got thermal efficiency of the design process is 0.9 or 19%. This is the actual Rankine efficiency, where we designed the steam power plant in the Aspen HYSYS in regards of actual Rankine system. While we also can analyze this, where we can analyze the steam power plant using the ideal Rankine cycle thermal, where we use the entropy of the working fluid using the parameters available. We can have the thermal efficiency of 0.2 Rankine efficiency, which is also known as the theoretical efficiency. So in comparison, we can see that efficiency of the actual Rankine cycle is lower than the efficiency of ideal Rankine cycle. To explain this further, I will pass the floor to Carl to explain this.
Okay, next. Okay, so the reason why the efficiency of is lower than ideal is because as the steam power plant is proposed is an actual condition which thermodynamic processes are somehow irreversible by stating that the mechanical friction and the heat losses might occur and causes efficiency loss. It was taken into consideration on Jashmen Reuben simulation that each stage of the Rankine cycle is associated with some irreversible processes, resulting the thermal efficiency calculated, which is the actual Rankine cycle, which is lower than the ideal Rankine cycle efficiency. However, the analysis of the steam power plant is made under ideal assumptions and calculations. These assumptions were made to make the analysis of the steam power plant more convenient. Next slide. So in conclusion, for equipment in our steam power plant, we have used the total of 1 pump, 1 boiler, 6 50 megawatt high-tech steam turbine to generate electricity, and for our heat exchanger, we have used 1 air-cooled condenser in order to achieve the desired net output of 280 megawatt of electricity to power up the new Lumut naval base. A heat engine, which consists of boilers, steam turbine, condensers, and pumps, is dependent to the efficiency limitation imposed by the second law of thermodynamics. So, in ideal cases, this heat engine would have a current efficiency of 30%. Meanwhile, the actual power plant utilizing the actual Rankine cycle, the calculated efficiency is only 19%. Although there's a shortfall of 11% of thermal efficiency, our steam power plant design is still able to generate the desired electricity. So, in order to increase the thermal efficiency, is to design a reheat Rankine cycle or design a regenerative Rankine cycle steam power plant, which is known to be widely used in the industry. So, next slide. For recommendations, there are three ways in order to increase the efficiency of Rankine steam power plant. Firstly, is by lowering the condenser pressure, which will subsequently increase the net work output. Next is by superheating the steam to higher temperatures. This can increase net work output and work input, thus increasing the efficiency. This is also making sure that the moisture content of the steam at the turbine exit is low. Finally, is by increasing boiler pressure, which will automatically raises the temperature of working fluid. And by doing so, this increases the average temperature at which the heat is being transferred to the steam, therefore increasing the overall thermal efficiency of the cycle. That's all. Thank you.